So we're looking at the potassium-argon, argon-argon methodology of gauging how much time has passed relative to the Earth. And sometimes they've tried this on the Moon. According to the assumptions foundational to potassium-argon, Ka-Ar, and argon-argon, Ar-Ar, dating of rocks, there should not be any daughter radiogenic argon, Ar-40, in rocks when they form. When measured, all argon-40 in a rock is assumed to have been produced by in situ radioactive decay of K40 within the rock since it was formed. However, it is well established that volcanic rocks, basalt, contain excess argon-40, that is, argon-40 which cannot be attributed to either atmospheric contamination or in situ radioactive decay of K40. Let's just take a look at what in situ means. What does in situ mean? In its natural or original position or place. Just in case you didn't know what that means. This excess argon-40 represents primordial argon carried from source areas in the Earth's mantle by the parent magmas, and it is inherited by the resultant volcanic rocks, and thus has no age significance. It's just moved around. And that's the problem with geology and uniformitarianism and evolution. They don't know the difference, and you can't tell the difference. So you have to disqualify the examination or the experimentation that you're doing on the basis of the possibility that these things could contaminate your experiment, but they don't. They just pick and choose the results that they want and throw out the ones that they don't, that don't situate themselves towards their point of view. However, are all other rocks in the Earth's crust also susceptible to contamination by excess Ar-40 emanating from the mantle? I would say so. If so, then potassium-argon and argon-argon dating of crustal rocks would be similarly questionable. How far deep do you go to find out if there's any potassium or magma or volcanic materials that could contaminate the experiment? So when muscovite, which is a common mineral in crustal rocks, is heated to 740 degrees to 860 degrees centigrade under high argon pressures for periods of 3 to 10.5 hours, it absorbs significant quantities of argon, producing potassium-argon ages, so-called, of up to 5 billion years. But you're heating it up. Only a few moments to heat it up. And the absorbed argon is indistinguishable from radiogenic argon, Ar-40. That's a potential defect, so I don't think this method is useful at all. In other experiments, muscovite was synthesized from a colloidal gel under similar temperatures and argon pressures, the resultant muscovite retaining up to 0.5% weight of argon at 640 degrees centigrade at a vapor pressure of 4,000 atmospheres. This is approximately 2,500 times as much argon as is found in natural muscovite. Thus, under certain conditions, argon can be incorporated into minerals which are supposed to exclude argon when they crystallize. So here's another possibility that really debunks this methodology to determine how old the rocks are. Patterson and all his entourage envisage noble gases from the mantle and the atmosphere migrating and circulating through the crust, so there should be evidence of excess argon-40 in crustal rocks. Noble gases in CO2-rich natural gas wells can find such migration and circulation. The isotopic signatures clearly indicate a mantle origin for the noble gases, including amounts of excess argon-40 in some CO2 carbon dioxide-rich natural gas wells exceeding those in mantle-derived mid-ocean ridged basalts, strongly implying that excess argon-40 in crustal rocks and their constituent materials and minerals could well be the norm rather than the exception. Dalrymple, referring to metamorphism and melting of rocks in the crust, has commented, if the rock is heated or melted at some later time, then some or all of the argon-40 may escape, and the potassium-argon clock is partially or totally reset, making it useless for accuracy. Thus, argon-40 escapes to migrate in the crust to be incorporated in other minerals as excess argon-40, just as argon-40 degassing from the mantle does. Excess argon-40 has been recorded in many minerals, some with essentially no potassium-40 in it, in crustal rocks: quartz, plagioclase, pyroxene, hornblende, biotite, olivine, beryl, cordierite, tourmaline, albite, and spodumene. The argon-argon method has also been used to confirm the presence of excess argon-40 in feldspars and pyroxenes. In a recent study, 128 argon isotope analyses were obtained from 10 profiles across biotite grains in high-grade metamorphic rocks, and apparent argon-argon ages within individual grains ranged from 161 Ma to 514 Ma million years. This cannot be solely due to radiogenic buildup of argon-40, but due to incorporation by diffusion of excess argon-40 from an external source, namely argon-40 from the mantle and other crustal rocks and minerals, as we were discussing. Indeed, a well-defined law has been calculated for argon-40 diffusion from hornblende in a gabbro due to heating. Excess argon-40, which accumulated locally in the intergranular regions of the gabbro, reached partial pressures in some places of at least 10 squared atm. Well, let's move on. This crustal migration of argon-40 is known to cause grave problems in regional geochronology studies. For example, in the middle Proterozoic Musgrave Block, northern South Australia, a wide scatter of potassium-argon mineral ages was found, ranging from 343 million years to 4493 million years, due to inherited excess argon-40, so no meaningful interpretation could be drawn from the rocks. Of the diabase dikes, which gave anomalous ages, it was concluded that the basic magmas probably formed in or passed through zones containing a high partial pressure of argon-40, permitting inclusion of the gas in the crystallizing minerals. Likewise, when argon dating was attempted on a Proterozoic granulite facies rocks in the Fraser Range, Western Australia, and Trangways Range, Central Australia, it was found that the granite, sapphire, and quartz contained excess argon-40 that rendered the argon dating useless because of ages higher than expected. The excess, notice expected, you should just not expect anything, just what you get is what you get. The excess argon-40 was probably incorporated at the time of the formation of the minerals, and calculations suggested a partial pressure of 0.1 atm AR in the Proterozoic lower crust of Australia, which extends over half the continent. So much for that. An argon-argon dating study of high-grade metamorphic rocks in the Broken Hill region, New South Wales, found widely distributed excess argon-40. Plagioclasts and hornblende were most affected. Step heating, argon-argon age spectro yielding results up to 9588 Ga. Wow. Such unaccepted ages were produced by excess argon-40 release, usually at 350 to 650 degrees centigrade and or 930 to 1380 degrees centigrade, suggesting excess argon-40 is held in sites within respective mineral lattices with different heating requirements for its release. We're not geologists here, so don't try to understand this in specifics, but we notice one anomaly after another that destroys the accuracy of this method. Thus, at crustal temperatures, which are less than 930 degrees centigrade, some excess argon-40 will always be retained in those trapping sites and minerals where it is held more tightly. A visible interpretation of these Broken Hill data was only produced because assumptions were made about the age of the rocks and of a presumed subsequent heating event based on lead and rubidium strontium dating. They compare the two methods and we find inconsistencies, we can't use it. So far, not a very accurate means of measuring age of rocks. When it is conjectured that accumulated argon-40 was released from minerals, causing a significant regional argon partial pressure of -3 × 10⁴ atm, domains within the mantle and crust have been identified and the interaction between them described, all of which is relevant to the migration and circulation of argon, and thus excess argon-40, from the lower mantle through the crust. The 6 domains are physically distinct units which exhibit wide differences in average physical and chemical properties, as well as structure and tectonic behavior. They are the lower mantle, between 670 kilometers, upper mantle and continental mantle, lithosphere, oceanic crust, the latter 4 constituting the Earth's crust. Each is a distinct geochemical reservoir. A steady-state upper mantle model has been proposed for mass transfer of rare gases, including argon. Rare gases in the upper mantle are derived from mixing of rare gases from the lower mantle, subducted rare gases, and radiogenic nuclides produced in situ. Assuming a 4.5 Ga Earth, it is claimed the lower mantle is assumed to have evolved isotopically approximately as a closed system with the in situ decay of these elements, adding to the complement of initial rare gases. Thus, some of the argon-40 must be primordial, not derived from radioactive K40. But how much is unknown? Again, unreliable. It is also claimed that potassium-40 decay in the upper mantle further increases the radiogenic argon-40, thereby a factor of about 3 compared with the lower mantle. But this also presupposes a 4.5 Ga Earth and doesn't allow for primordial argon-40 in the upper mantle. The bulk of argon-40, the lower and upper mantles, could be primordial, but there is no way of knowing, as primordial argon-40 is indistinguishable from argon-40, and it floats around all over the place. You get the picture here without knowing all this expertise here. Because it is known that excess argon-40 is carried from the mantle by plumes of mafic magmas up into the Earth's crust, it is equally likely all the earthquake activity and volcanic activity, constantly changing things, you see. It is equally likely that much of the excess argon-40 in crustal rocks could be primordial argon-40. We don't know which is which. You weren't there. Thus, we have no way of knowing if any of the argon-40 measured in crustal rocks has any age significance. Again, additional to the primordial argon-40 from the mantle is argon-40 released from minerals and rocks during diagenesis and metamorphism, so that there is a continual migration and circulation of both primordial and argon-40 in the crust, which is reflected in their presence in CO2-rich